The big five are fundamental equations used in almost any kinematic problem. But what are they, and why are they so useful? Before I start, I want to just specify what each variable means. If you don't know any of these variables, make sure you watch my video explaining kinematics simply for beginners before you watch this video. The reason why the big five are so important is because they can be used to solve any kinematic equation that has constant acceleration. Constant acceleration just means that the acceleration does not change. Every equation has four variables, and each equation is a different combination of the same five variables. So each equation is just missing one variable in it. This means that if you know the value of three variables, you can use these equations to find the value of the other two variables that are missing. For example, if you have time, acceleration, and initial velocity, you can find final velocity using this equation. And you can find displacement using this equation. Let's look at some practice problems. So the first problem here, problem 1, a car going 20 meters a second sees a red light 40 meters ahead and starts to brake uniformly. What is the acceleration? All right, so I have a drawing here, and then also our three knowns that we have. So we know initial velocity, we know displacement, and we know final velocity. We're trying to find acceleration. So that's the one that is unknown. First off, we're just going to set a direction for everything. So I'm going to put an arrow right here, just draw a positive sign, and then I'm going to set F, which is going to be equal to forward. It's going to be positive, okay? So everything that's in that direction is going to have a positive sign next to it. And I forgot to put meters here. Meters there. And of course, VF, since it's 0, you don't have to put a direction because it's in neither. It's neither forward nor backwards, so there's no direction. All right, so what I'm going to do next here, so I'm just going to set acceleration into the negative direction. This is because if we start off at 20 meters a second and we go to 0 meters a second, then we're going to end up slowing ourselves down, right? So therefore, acceleration is going to have to be backwards. Sorry, first thing we're going to do here, so we're going to put in the equation. So this is the one we're going to use. VF squared equals VI squared plus 2 acceleration delta x. And then VF is equal to 0 because see 0 and 0 squared is just 0. And then VI was 20. V squared 20. So I'll just write 20 squared. And then it's going to add 2 times and then 40 because that is delta x and then acceleration. And then of course there's a positive there and a positive there. So then we're going to rearrange this. So this is going to go to this side. So then we're going to get 20 squared on the other side, so negative 400. Because it's moving to the other side, it switches signs because you're subtracting like 400 on both sides. Sorry, it's 80 times acceleration. And then, because you squared it, it's like squared right here, squared right there. And this is just meters, 80 meters times acceleration. Then you're going to divide by 80 on both sides. So then you're going to get negative 5 meters a second squared equals acceleration. And then if we remember from before, so we set positive to forward, right? So since this is a negative, that means it's going to be backwards. So acceleration is going to equal 5 meters a second squared backwards. So bracket, and then BCK for backwards. There we go, and that's all. Problem 2. Darius is cruising down a hill on his bike going 10 meters a second. He's accelerating at 2 meters a second squared in the same direction. How far would Darius travel in 5 seconds? All right, so I have problem number 2 drawn out here, so we can see there's Darius going down the hill. So for our knowns, we have initial velocity, which is positive, so I set down to positive here. So 10 meters a second positive. Acceleration is 2 meters a second squared positive. Time is 5 seconds, and then we're trying to find displacement. So the equation we're going to use is delta x equals vi times delta t plus 1/2 delta t squared times acceleration. So let's fill in for our values. So delta x, I'll draw the arrow at the top there, is going to equal 10 meters a second times 5 seconds plus 1/2 5 squared, and then of course times 2. Okay, so then if we bring all this together here, then we're going to get delta x equals 50 meters plus, well, these two things cancel out, and then we're just left with 25 meters. So then delta x equals 75 meters. All right, and that's the answer. So displacement is 75 meters. All right, then there's one other thing I forgot to do here. So because it's a vector, we have to set direction, right? So be 75 meters down. Problem 3. Jenny ran the 100-meter sprint in 10 seconds. Assuming her acceleration was uniform, what was her final speed? Okay, so I'm going to do problem number 3 now. So I have all the unknowns and knowns written in here. So what we're trying to find is VF. So VF right there. We have time, we have displacement, we have initial velocity. So the one we're going to use is delta x equals 1/2 delta t. And then remember these brackets. You always got to do the brackets. Plus VI. Okay, and then draw on the arrows. So basically what this is saying is that displacement is going to equal average velocity times time. Because this 1/2 right there, you can also write that 1/2 as like divided by 2. So if this wasn't there, you could write it as divided by 2. So then this right there would be to find average velocity, which you'd then multiply by the time. But you can also write it this way. Either way works fine. And then I'm going to fill in all the numbers. So positive 100, and then meters equals 1/2 times 5 seconds. And then VI is equal to 0. So we can take that out. And then it's just VF. Okay. So I'm going to multiply these two things together. So that's going to be 2.5. And then, so yeah, this is 2.5. This is 100. And then this is VF. And I'm going to divide by 2.5. So this will equal 40. And then it's meters a second. So 40 meters a second positive equals final velocity, which you can then, if you remember from before, so positive, east is in the positive direction, so that means velocity is going to be in the east. So 40 meters a second, bracket, east. There we go. And that would be how you'd find it. So I have 6 practice problems here. The first 3 are relatively easy. You should be able to do it based off what we've learned here today. The other 3 are a little bit harder, especially the last one. So the first 3, I'll have videos explaining how to do it. And then the last 3, I'll have videos as well. They might be separate though. So check my playlist on 1D kinematics to find the solutions and then also answers. And then please leave any comments you have, or ask me any questions you have in the comment section.